Today, we are going to talk about binary trees. Before we go on, let's talk about the motivation, why we are concerned about binary trees. In the last lecture, we stated we would like to build efficient sets and dictionaries because we could solve numerous problems with dictionaries. And we made the following operations O1 by utilizing random access memory called RAM. So we may find O1 and insert and delete all these three operations O1 by using random access memory. And to do so, we talked about two methods. The first one was chaining, and the second one was open addressing. And are we done? So what is the time complexity of the following operations using hashing? So find find the item with the minimum value among all the items stored in our dictionary, and find max, which finds the item with the maximum value. These two operations require O(n) time complexity because the items we have stored are not sorted. We saw this in the sorting class. And the thing is, we use find mean and find max quite frequently. Thus, although we made insert, delete, and find operations O1, find mean and find max are going to take O(n) time complexity. And because we're going to use these operations quite a lot, in the end, the efficiency is not that good. Therefore, we are going to make all operations efficient using trees in the consecutive lectures. And because we are going to use trees to make all these operations efficient, we first need to have a look at what trees are and how we can use trees. In fact, what we are going to do is we're going to make find, insert, delete, and find mean and find max O log n. All right, so you are familiar with this time complexity. We saw this time complexity in binary search class. Anyway, we sacrifice the find, insert, and delete operations to be log n rather than O1. But we could make these two operations much more efficient from n to log n. So overall, all the operations are going to take O log n. So on average, every operations are going to take time complexity O log n rather than O(n), all right? Thus, we'll first have a look at binary trees. So what is a binary tree? Figuratively, binary trees look like this. So there is a node like this, and one node can have maximum of two children like this. And some nodes can have one node as child or no child at all. And we'll define binary trees more formally. There are two definitions, in fact. The first definition is recursive definition. I mentioned this definition in the previous lecture, one of our previous lectures. We'll talk about this again here. A tree has a root and a list of branches. And a tree starts at the root. And each branch is itself a tree. So we are defining tree using tree. So tree is connected to another tree. A tree with 0 branches is called a leaf. So these green nodes are called leaves. And there are a second definition that is called relative definition. Each location in a tree is called a node. So as I mentioned, these values, these things are called nodes. And each node has a value. Although we have integers in our example, these nodes can have other values like characters or strings. And one node can be the parent or child of another. It is similar to the recursive definition. Each branch is itself a tree. And the top node, we call the top node a root node. So this is relative definition. Either of definitions is okay. And there are some features in terms of binary trees. For every node except the root, there is exactly one edge pointing to that node. So here you can see there's just one node coming inside to this node. And this node has just this one edge that points to this edge, this node. So that is what it talks about. And for every node, there is a unique path from the root to that node. So in this example, there is just one path to reach the node with the value 3 from the root. We have just this one root. We have no other roots. That is another feature of binary trees. And we define the depth of a node is the length of the path from the root to that node. We're going to have a look at depth and height in the following slides in more detail. And the height of a node in a tree is the length of the path from the node to the deepest leaf. Okay, let's have a look at what it means. So the first node with A, this is called root. Actually, this is not a binary tree. This is just a general tree. In this case, the depth is 0 and the height is going to be 3 because we have 3 other nodes and this is the deepest leaf from this root. So that is why its height is 3 and the depth from the root is 0 because it itself is root. And when it comes to B, the depth is 1 because it is one edge away from the root and the deepest leaf from this node is F or G and it takes one edge to reach there. It's very simple, right? And when it comes to C, the depth is 1 as B because there is just one edge to reach root. And the deepest leaf is 0 because the node with C itself is a leaf, okay? And think about D, E, F on your own for a minute and I'll show the answer. All right, I'll give you 1 minute and think about these 3 nodes. All right, thank you for sharing your answers. So when it comes to D, the depth is 1 because we have one edge. And the height is 1 because we have just one edge to reach the deepest leaf from this node D. And when it comes to E, it has one edge to reach the root, so the depth is 1. And the height is 2 because we need to pass 2 edges to reach the deepest node, K. So regarding this concept, do you have any questions? Okay, let's move on. And there are numerous applications of trees itself, other than constructing efficient dictionaries and sets. For natural language processing, 자연어 that people are using, humans are using, we could interpret or analyze a sentence in this form, like subject, noun phrase, verb, determiner, noun, like this. If you are interested in artificial intelligence or deep learning and natural language processing, we're going to see these a lot. And another application is when we're structuring documents, we could structure documents in XML format, and it has a tree representation. And if you are interested in internet, in web development or things like related to the internet, then you are going to see this a lot. All right, from now on, let's talk about tree traversals. To perform useful operations below, we need to travel through trees. Sometimes you want to count the number of leaves in a tree. And sometimes we want to count paths from one node to another. And sometimes we want to manipulate the values of nodes. When we want to do these kind of operations, we need to travel through the nodes in a tree and manipulate the values of a node. And there are 3 ways of tree traversals. The first one is called pre-order traversal. And this means that a node is processed before its children. And in-order traversal means that a node is processed between its left and right children for binary trees. So we cannot define in-order traversals for other types of trees, but only for binary trees. We're going to have a look at concrete examples of pre-order, in-order, and post-order traversals in the later of this slide. And post-order means that a node is processed after its children. All right. So let's say we have this binary tree, and we want to travel through all the nodes in the schema of pre-order. In such case, we first need to visit the node and then visit the left subtree recursively. And then we're going to visit the right subtree recursively. This is the convention. In fact, you could visit the right subtree first. However, that is not our convention. So we're going to visit the left subtree first. So in this scheme, the pre-order traversal result is going to be, you first visit F, because we start from the root, and we're going to visit the node itself first, and then process the children of this node. So we are going to visit F first, and then go to the children, the left child, that is B. And when we reach here, we're going to do the same thing. We first visit B, and then we visit the left child, that is A. So that's why FBA comes here. And after we process the left child, we're going to process the right child, that is D. So we came from root, B, left child, and the right child. And when we reach here, we're going to process the left child. So that is going to be C, and then we come back here and then process the right child, that is going to be E. So here, F, B, A, come back here, process the right child, D, and then left and right. And in the perspective of F, we processed all the children on the left side. And what we are going to do is process the right child. So after we travel through all the children on the left side, we're going to go to the right. That is going to be G. So F, B, A, D, C, E. Up to this point, we covered all the children on the left side. And we're going to cover the right side. That is going to be G. Because this one has no child on the left side, we're going to go to the right side directly. That is going to be I and then H. Okay. So tree traverser itself is recursive. And we are going to implement tree traversers using recursion. And very simple way to find out the pre-order traversal result is drawing this diagram. So we start from the root and draw this line like this. And we want to wrap all the trees like this. And when we pass the left side of a node, then we write down the node's value. So we start from here. When we pass the left side, we write down F. We come over here. When we are on the left side of this node, we write down B and go on and on. And F, B, A, D, C, E, G, I, H. So that is how we find out the pre-order traversal result. Okay. Now we're going to have a look at in-order scheme. In the in-order scheme, we're going to visit the left subtree first and then visit the node itself. So in this case, when we start from F, rather than visiting F first, we are going to process the left part first and then the node itself and then the right part. So visit the left subtree recursively first, and then visit the node, and visit the right subtree recursively. So can you guys guess what will be the result of in-order traversal results? The pre-order traversal result is A, B, C, D, E, F, G, I, G, H, I. So how is it A, B, C, D, E, F, G, H, I? So when we start from the root, rather than visiting this node, we are going to process the left part first. So we go to the left part and we do the same thing for this node. So when we come over here, rather than visiting this node, we are going to have a look at the left child first. So that is going to be A. And when we come back here, we are not done. We need to have a look at we need to process this one and then go to the right part. That is going to be D. However, we are not going to visit this node, but go to the left child first. That is C. And so up to this point, we have visited A, B, C, and we come back here and visit D and go to the right side. That is going to be E. All right. So when we finish the left children, we come back over here and we visit this node that is going to be F, and then go to the right side and visit all the nodes here. However, there is no left child. So we are going to visit this node G and then go to the right part. And here we have left child. So we are going to visit this one first and then come back over here and visit this node. So it is going to be A, B, C, D, E, F, G, H, I. All right. So we can find out the pre-order traversal results more easily using the same scheme. In the case of pre-order, we write down the value of the node when we pass the node on the left side. However, when it comes to in-order traversal, we're going to write down the value of this node when we are passing through the bottom of this node. So we are going to wrap this tree as follows. And when we're passing the bottom side of the node, we're going to visit that node. So when we come over here, it is going to be visited, not visited yet, visited, like this, all right? And when it comes to post order, the thing is somewhat different. We're going to visit the left part first, and then the right part, and then the node. And the scheme is we are going to visit the node when we are passing the right side of the node. So in this case, when we wrap this tree, it is going to be A, C, E, D, B, H, I, G, F. Okay. So in summary, we have talked about 3 ways of tree traversals. The first one was pre-order. When we are doing pre-order traversal, we're going to visit the node when we are passing the left side of a node. And we talked about in order. In this case, we're going to visit the node when we're passing the bottom side of a node. And when it comes to post order, we're going to visit the node when we're passing the right side of the node. Okay, so you just need to remember pre, in, post. This is very simple. And the convention is we visit the left part first. Cool, let's move on. And from now on, we're going to implement trees and tree traversals. All right. We're going to define trees first. Defining trees is quite simple. We're going to use similar schemes that is similar to linked list. We're going to define a node and connect those nodes to form a tree. So the tree class is very simple. We're going to receive a label and then branches. Here, this is general tree. And from general tree, it is very easy to form a binary tree because here we can have multiple branches. But when it comes to binary tree, we just allow 2 branches, left and right children. So we're going to first implement general tree and then reduce this general tree to binary trees. All right, so we're going to assign the given label to the label attribute. And we're going to put these branches into this branch attribute. That is all. However, we just need to make sure that every branch has to be tree. So this is to make sure that these branches are trees as well. So that is all. It is how we implement trees. And I'll show you some test cases. So how do we actually form trees using this class? We can form tree like this. So tree with 3, this is going to be the root. So this is how we define a tree. And in fact, it looks like this. So first, the root is 3, and these are branches. And these branches look like this. The first one is a tree, another tree with no leaves, and another tree. This one looks like this. So this one has 2 leaves, 1 and 1, and it has the value 2. So it itself is another tree, and it looks like this. Okay. So when we first had a look at linked lists, we first defined a node and made linked list formation construction easy by receiving some values, initial values, like items, like this. And we're going to do the same thing for trees in the later of this course. We're going to receive pre-order and post-order results of nodes, and we're going to form trees, okay? So that is what we are going to do in the later of this course. And another feature we need to support is, you can see the label of a tree like this. And we want to check whether this node or tree is leaf or not. In this case, this tree has other branches or leaves, so this is going to be false. And when we have a look at the first branch, which is this one, and call this leaf function, leaf method, and it is going to be true, right? So we are going to define this method as well. And it is very simple to implement. You just need to check whether this tree has branches or not. So we're going to just check whether self branches is empty or not. Empty branch, empty list corresponds to false. So if this one contains some values or other trees, it is going to be true. Okay. So I'll give you some PPP exercises from now on. So this is how you define tree. That is very simple. And can you implement this function, count leaves? So this function receives a tree like this, and then counts the number of leaves. So in this case, when we pass this tree, it is going to be 3 because it has 1, 1, 1 leaves.